to introduce Jinho Baik from the University of Michigan. And he'll be speaking about multi-point distributions of the periodic TASEP and differential equations. So please start, Jinho.
Hello?
Jinho, did you hear me?
Yeah, I think my internet was a little bit unstable. Just a moment. Yeah, I hear you now.
Okay, well, yeah, we just introduced you, and so please start when you're ready.
All right. Okay. Sorry. Yeah. Okay. Thank you very much. Thanks for the kind invite. So the plan here is that I'm going to talk in about two related things. In the first part, I'm going to talk about random growth models on the ring instead of on a line, and discuss the fluctuations. In second part, I will discuss the deterministic differential equations that these models, whether their limits, the fluctuation limits, satisfy. So this is all joint work with Zipeng Liu, who is in University of Kansas, and Andrei Prokhorov, who's a postdoc at Michigan, and Guilherme Silva, who is in Brazil. He's at University of São Paulo. He was a postdoc in my department, and he went to São Paulo about 2 years ago. Yeah, so the first part, the random growth models on the ring. So I will consider TASEP on a ring. So TASEP on a ring, or equivalently, we can think about periodic TASEP, spatially periodic TASEP, or also equivalently, we can think about corner growth models on the ring. And then here the important parameter is the ring size, which I denote by L here. And we'll consider this L to be very large. Okay, so we'll take the L to be large. We'll take a limit L to infinity. When we do that, we'll assume that the particle density remains as constant. The particle density is always throughout this talk, it's going to be half. Okay, right. So in the KPG theory, so we'll consider the fluctuations, high fluctuations. So in the KPG theory, on the whole line, there's a 1 to 3 scaling relationship. So in particular, the spatial correlation, the point-to-point correlation is of order T to the 2/3. So if the ring size L is about the size of L to the, oh, I'm sorry, this is a typo, L to the 2/3, this should be 2/3, L to the 2/3. And then that means that the all points on the ring are critically correlated. Right? This was what suggested by Agua and Spohn in 1992. So intuitively, you can think that when time is short, in the sense that, sorry, this is typo, L is T to the 2/3, so T is L to the 3/2. So when T is smaller than L to the 3/2, the ring size do not affect the fluctuations, and then this TASEP on the ring, at least from the point of fluctuations, should essentially look as TASEP on the line. On the other hand, if the time is much longer, much bigger than L to the 3/2, then these spatial correlations between all particles, all locations will have become correlated, and that the correlation becomes strong. So we may expect that all locations have strong correlation. So the critical scale is, and T is L to the 3/2, and at that point, the ring size begins to have an effect on the fluctuations of the height function. So we are going to take that kind of limit. So that's why we call it relaxation time limit. So we'll be interested in the fluctuations of the height functions as both the ring size and time are large, satisfying the relationship that the time is of order L to the 3/2, but while still keeping the 1 to 3 KPG scaling exponents. So that means that the height, position, and time should be a 1 to 3 ratio, meaning that T to the 1/3, T to the 2/3, and T, but converting them into L is L to the 1/2, L, and L to the 3/2 relationship. Okay, so we'll we'll scale our high position time in this scale, and then assume that the time is L2 3 halves, what we're choosing here as well. And we take the limit and look at the fluctuations. So the fluctuation limit will depend on the rescaled time parameter, which is T over L2 3 over 2. I just put 2 there just to make the formula a little bit nicer in the end. So when this rescaled time parameter becomes infinity, it corresponds to the case when T is much greater, and little t tends to 0 corresponds to a case when capital T is small, so that's a short time limit. So here's a result. So I will consider that we can think of this one in any random growth models or any interacting particle systems. But here we'll consider the TASEP because that's the case that we can compute. So TASEP on a ring, we'll start with the step initial condition. So that with the, there are exactly L over, so we'll assume L is to be even and there are L over 2 particles. Sorry, so the initial condition is taken to be this one exactly. So I call it step initial condition, but if you change that to the periodic TASEP, that would be in the one period. We have particles and holes and particles and holes and so on and so on. So this part looks like a step initial condition, but on the other hand, this part will create a shock, right? So that's the initial condition we are going to start with. The theorem that we could obtain was that with the ZPMU was that the associated height function, this L denotes a period again, and you position and time, you scale as L and L to 3 halves, and subtract the average, and divide by the fluctuation, which is L to the 1 half, and this one converges as L tends to infinity in the multi-point distribution sense. So if you take the joint distribution of this one, where X and T can be anything, so joint distribution not only in the positions, but also in time as well, that will have a limit. And that limit is also very explicit. And then I will describe that a little bit.
So, may I ask a question?
Yes.
So in this result, this limit is different from, let's say doing the same thing on the real line and taking periodic initial condition.
Yeah, it's different. Yes, that's right. Yeah. So that's what I want to discuss now.
Okay.
So yep. Yeah. So it will be different because of the ring's size impact, right? So the limit. Yeah. So I'll probably list that in the next slide. So the limit is also obtained for the flat and initial condition and some general initial condition as well on the very technical conditions. And the same result was obtained 1.2 case by a prologue in a physics paper. And also this is for continuous time TASEP, but the discrete time TASEP and also polynuclear growth model, one can also obtain the same limit. So the limit found in the multi-point distribution of the limit should be the corresponds to a periodic KPG fixed point that should have this spatial periodicity. So it should be the periodic version of the KPG fixed point. Yeah. So so we expect the following. So we only proved for the 1.2 case at the moment, but we expect the following. So when you take this time, rescale the time and time to be 0 versus rescale time to infinity. So in one case, one should go to the KPG fixed point, and the other case becomes the location would not appear in the limit, and then the whole thing just goes to the Brownian motion. So this one just corresponds to that all positions become strongly correlated, so it works, behave like just one particle. And then here, this H of xt denotes the KPG fixed point, which is the limiting two-dimensional field for the infinite line case, starting from this periodic periodic initial condition, periodic step initial condition. Yeah, so I guess this one doesn't really answer the Milton's question, whether this one is different from the KPG fixed point starting with the periodic step initial condition. Now I come to think about it, I never actually checked whether they are the same or not. But I think they are different. Yeah, I think they are different, but actually I never actually checked the answer there. Yeah, but anyhow, so this is what one sees if you take the limits. So if you take epsilon to 0, so that is this time tends to 0 case in this picture. So the dotted lines are the 1-point distribution of this ring model at various times. And then there are two different things corresponding to one particular time, one particular location and another location. One is the where the shock do not emerge, and the other one is where the shock appears. Because of the initial condition has a little bit of the shock initial condition. And as time tends to 0, one goes to a trace rhythm distribution, and the other one is the two trace rhythm distribution added together. That's where the shock location, the high fluctuation is the sum of two independent trace rhythm. And on the other hand, if you take this T to infinity, this T to large, and this dashed curves eventually becomes this Gaussian distribution. Right. So the this 1-point distribution interpolates GUE trace rhythm distribution and also the Gaussian distribution, or the in some other cases of the location is a GUE trace rhythm plus trace rhythm distribution to Gaussian distribution, that interpolates and those things. Right. So how one can prove this one? So we use the exact solvability nature. So the periodic TASEP is a Markov process on the following chamber. So instead of ring, we made it to periodic, especially periodic process. So the last particle xn should be confined with x1 plus L. So that's an extra condition there. And the transition probability satisfy the Kolmogorov-Ford equation. This is the case when n equals 2. This is 1 point left, and this is 1 point x2 minus 1 is on the left. But then the condition is that during all this time, all this process, all the particles should remain in the chamber. So this is a delta terms in the equation. This is a linear differential difference equation, but the coefficients are not constant, but rather delta coefficients. So if the delta terms are not there, then this is very easy equation, but then delta term is the one that makes things difficult. But the point is that even if with these delta terms present, one could solve this differential difference equation and find the transition probabilities in a very explicit way. And that was done for the case of the whole line when this L is infinite case by Schutz in 1997. The way he did was that he adapted the Bethe ansatz. That is that so this delta, the differential difference equation with the delta coefficients, you replace it by the delta terms by 1. And then we got just free evolution equation, which is very easy to solve. But then these delta terms that you removed, you replace them by a boundary condition that the solution should satisfy. So instead of so delta equations, you replace by free evolution equation plus boundary conditions. And the Bethe's method is that if you generate large number of solutions to free equation, then there is a little bit of semi structured process of how to find a solution, how to cook up a solution that satisfies the boundary condition and also the initial condition. That's rather difficult to check in some cases, but for this particular case of the TASEP on the line, Schutz was able to do that. But however, this finding the transient probability is just one thing, and then from the transient probabilities, one has to go to the actual distribution of a particle at height. Then we have to sum up this transient probabilities of all possible locations, and that is usually the difficult thing. And if your formula of the transient probability is not compact enough, then one cannot do that. But it turned out that the formula that Schutz obtained was compact enough to be able to reproduce the famous result of Johansson on the TASEP, where he was able to obtain the Fred-Terminus formula for the one-point distribution using a combinatorial method. But solving this Kolmogorov equation now could reproduce the same result. And then this idea was then used in further models very successfully. First of all, it was then used to solve not the step initial condition for general initial condition for the TASEP, and then the later Tracy and Widom in their work on extending the TASEP to ASEP, they extended this Schutz method to the ASEP, which was a big deal in late 2008 and 2009. And that was the basis for being the Amir Cohen and Quasar's work of solving the KPG equation from ASEP. So that was the case of the whole line. And then for the periodic model, then there have been results of solving this Bethe-Ansatz equation, but none of them were enough to produce the formula for the distribution functions for the symptomatic analysis. But then in the prologue in 2016, and also as Zipeng and myself, then we were able to solve this equation in a rather compact enough form to be able to go to the distribution function formulas. So the formula looks like this. So this is a transient probabilities formula. So Schutz formula looks as follows. So assuming that there are only n particles in the whole line on the line, so going from y to x in time t can be written as n by n determinant, whose entries are just explicit in this form. Here's it's a integral, complex integral on a contour. Contour can be taken to be a circle, and it should contain the origin but not the point -1, for example. I'm sorry, it contains -1 but not the origin, I think. And then this initial condition and the final location comes in this particular form. So if you want to change that to the periodic TASEP, what it turned out was the following thing. So forget this Z for now, but look at this inside this determinant. That inside determinant is basically taking this integral and then replaced by a sum. So instead of integral, we are doing the sum, the discretization. And this DZ is out there just to make this discretization a little bit more flexible. But the key point is this sum here. The periodic TASEP transient probabilities should satisfy this relabeling of the particle properties. Because of the periodicity, you could have starting initial condition y, you could go to location x1, x2 to be your target points, or you could relabel saying that, oh, you should go to x2 and x1 plus L to be your different particle labeling. So it should satisfy this sort of something like this several periodicity conditions, and this second formula is making this discrete sum over a particular trace of points of W, which you described in here, turns out to be the right way to achieve this periodicity of semi-periodicity of the transition probabilities. Here the sum is we are discretizing this contour by these points, but these points turned out to be a solution of this algebraic equation. Here the Z is this outside integral that is just there to be for flexibility. Essentially, this is a polynomial of degree L. There are L points, and these are in these dots. Then you have to take the sum over. And then this W satisfying this algebraic equation was the source that one could check this periodicity. If I change my X and Y to be certain new locations, then it creates some kind of a new term coming up here, W1 plus 1 to some other powers, and then W to some power. That power turns out to be using this equation, then that term can be removed. Right. So in a sense that the whole line problem versus a ring problem, the simple Fourier transform theory seems like a Fourier transform versus Fourier series, and here the whole the contour, continuous contour problem becomes these discrete points. That is the effect of in terms of formulas. So using this transition probabilities, then one could obtain the multi-point distribution formula, which is actually the harder part of the analysis. But once you do that, then one can take the limit L to infinity, and one could obtain the n-point distribution of the periodic KPG fixed point in the following form. So if you look at the n point in the space and time distribution, and then it is given by this m integral formula, which involves some explicit function c and some Freedom determinant. And then this Freedom determinant involves another discrete set, which is the sort of limit of these sets, which turns out to be the solution to the following equation, e to the minus z squared over 2 is equal to a certain constant. So these sets, the set of the roots are plotted in this black and white dots here. The time. Right, okay, so that's the first part. In the second part, I want to talk about slightly different or related thing, which is the from that now formula of the limiting n-point distribution functions. It turned out that they are related to very deterministic integrable differential equations. So I'm going to talk about those equations for the KPG fixed point itself, and also the periodic version of that KPG fixed point. Right, so to begin with, let me just recall the Trachy-Dam distribution. So if you look at the KPG fixed point with the narrow wedge initial condition, then it satisfies the invariance of the one-point distribution. So at any x and t, if you rescale properly, then it has the same distribution as just one has a same distribution, which is the GUE Trachy-Dam distribution. So if you define the f of c to be the distribution function, that is a Trachy-Dam distribution, and that has several different formulas. So one of them is the determinant of the area operator. And it's a function of c. And if you take a second derivative of the log of the function, that is the well-known result of Trachy-Dam in 1994, that it is u squared, where u solves the Penn-Levet-2 equation, which is this ODE. And this ODE is one of, there are 6 Penn-Levet equations. This is one of them. The second one, the pen-level equations are, this second pen-level equation is rather simple looking formula, but the other ones are very complicated. But the point there is that even though they are nonlinear second order ODEs, they are integrable in the sense that they can be solved exactly using isomonodromy method. So there is a procedure of finding the, solving the equation even though they are nonlinear using some nonlinear transforms. So so that was the KPG fixed point on the line with 1 point. If you look at the multi-point, especially, sorry, where is it? So if you look at the equal time and multi-position, so Quastel and Remenick obtained the following result. So they considered the KPG fixed point with a quite general initial condition. And then look at this 2m+1 variable function, which is you take the time to be fixed, but the locations and the height should be arbitrary. And consider this as a 2m+1 variable function. They started to looking at the equations, differential equations that is the derivatives of f, log derivatives of f will satisfy. And what they were able to show is that with arbitrary initial condition, this function will satisfy the so-called matrix KP equation. So KP equation is a well-known integrable PDE, which involves a third order derivatives with respect to the variables. So here's a t plays a role of time, and this this xi's and then hi's work as spatial variables. So these scalar KP equations are the one that is well known. So scalar KP equation is a 3-variable equation with the time and 2 variables for the position, so t and x and h. And the Quastel and Remenick's version is that extended that to matrix version, where the xi's and hi's are allowed to be multivariables. So this is so what they showed is that this KP equation is the equation that corresponds to the KPG fixed point for arbitrary initial condition. So this is KPG fixed point. So right, okay. But however, if you take the special initial condition, say narrow wedge initial condition, then this KP equation becomes much more specialized. So in particular, if you take this to be m to be 1, so there's t and x and h, and then looking at this KP, and together with the narrow initial condition, and then this 3-variable equation can be reduced to a 1-variable equation, and that is exactly the pen-level 2 equation. And there have been some other results for other cases, for the narrow wedge case, namely that if you take time to be just fixed, rather than thinking as an equation involving time, but rather time is fixed and looking at the equation between just x and h relationships. So then that is the fixed time, but thinking this x as now a time variable, that's an array2 process. And for that array2 process, the Treasury with them had obtained a matrix ODE, and also Adler and Van Moebeck also obtained some very complicated PDEs. So there have been results of this type, but this Quastel and Remenick's work is the one that identified this KP equation as the primary object. So now what I want to do here is that now instead of thinking this time to be just 1 for all, I want to take this time to be different as well. But then we'll have to assume that the initial condition is this narrow wedge initial condition, or the periodic narrow initial condition in the periodic KPG fixed point case. So in that case, there are formulas for the limit, the KPG fixed point. There is a one by Zipeng Liu for the KPG case, and then a periodic KPG case is slightly different. So they involve all this outside integral and then this of this d and then c and d, where c is a very explicit function. So it's not interesting, but there's a key point is its function d. And this d, this zeta is a outside variable, which we always fixed. And then this d will depend on this x and t and h, these 3m variables. And then they are all given by the Freudom determinants. So we'll think of this d as a function of 3m variables, positions and heights, and then, positions and times and heights, while this zeta is just auxiliary variable that is fixed, that we are not going to be interested in. So then the results of that considered with Prokhorov and then Silva is the following. So for both KPG and periodic KPG fixed point, assuming this narrow wedge initial condition, this D, which is the component of this multi-point distribution, if you take a log and then take this positional derivatives, it can be written as a product of two vectors, so dot product of RMP, and RMP are vectors, and this RMP will satisfy the three different systems of differential equations. Okay, in the following, we have to replace t by reverse the time, and also I'm going to use notation y for the height because that looks a little bit better. And then this partial respect to t means that actually sum of all partial respect to time, and this is sum of all heights and sum of all positions. So there are three equations. The first one is depending on which pair of variables that we're looking at. The first one will be x and y, position and height, and this is a position and time. And then the third one is all position and height and time all together. So using a position and height, and thinking this height as a time, but as a complex time, they satisfy this rather simple looking system. But one has to remember that this p is a vector, and y partial with respect to y means that partial of y1 plus partial of y2 and all this sum. And this looks very close to the nonlinear Schrödinger equations, which is well-known, one of the most fundamental integrable differential equations. So the scalar version of NLS would be, here's a complex time is needed, and then this is a second derivative with respect to x, and then this is a cubic term, there is a kind of cubic term. And remarkably, the same equation also appeared in the work of Pierre Ladoucelle and Krajenbrink in their study of weak noise theory of KPG theory, KPG equation. On the other hand, if you couple x and t, then we got the coupled vector modified KDV equations, which involves a third derivative of respect to x. And then this term looks like a version of this. And also, if you combine all x and y and t together, and then instead of looking at RMP, you swap them around and make a sort of matrix out of them. And then that matrix satisfies this matrix KP equation, which is written here. And in this equation, if you set all the times to be equal, then this matrix KP becomes the matrix KP of Quatermain and Riemann. And then also one can, for the KPG fixed point case, there are two more systems extending the Presudan's work and also the Adland-Venmo KPD as well. Right. So then, so how do we relate to these integrable differential equations from these random determinants? So there'll be only two slides here. So the proof is based on the fact that the random determinant is so D is a random determinant of an integrable operator type, which itself is a very interesting theory. So an integral operator is an operator on some L2 space on the contour in the complex plane. Well, it can also be a discrete set as well, of the following form. So the kernel is of the form that the top. So there are 2m. So this m could be any number. It has nothing to do with this m point distribution that we discussed, but okay, there are scalar functions, fi's and gi's, and out of them you build this multiplication, fi of u and gi of v, and then just add them together and divide by u minus v. So this looks like a some kind of Hilbert transform type formula or Cauchy transform type, where just to ensure that this k is non-singular when u and v are equal. And this type of operators were around, but in the systematic way was introduced by Izergin and Krapin and Slavnov in 1990. And they coined the terminology integral operator. They appear in lots of places in random metric theory and so on. So for example, the Trace-Udam distribution is given in terms of Airy kernel. And Airy kernel is an example of an integral operator because it can be written in this form here. Airy kernel is of this form, and this top is, this is V. So function of U times function of V plus function of U and function of V. A key feature of that is that of the integral operators are following. So if you denote M by the multiplication operator by a variable, so M is a multiplication variable that M of H, if H is a function on the contour, M of H is just variable times of H. If this is M is that, then K is an integral operator, means that if you take a commute K with M, so Km minus Mk, so so this will give a kernel given by K of uv times v, and this is U times K of uv. So that means that we have just basically multiplying U minus v to the left-hand side, and that is this this result should be this sum of this FIU and GIV, which is a finite rank operator. So integral operators are the operators that do not necessarily commute with the multiplication operator, but the commutation with the multiplication operator is finite rank. So it's rather nice class of operators. And the property of that is that I want to mention two facts. One is that if K is an integral operator and 1 minus K is invertible, then it's resolvent. Resolvent is this one here, 1 minus K inverse times K, is also an integral operator. It's not difficult to prove, but that's an interesting thing. Why is it relevant to us? That's because that we are taking log of random determinant, so log of determinant 1 minus K, and take some kind of derivative, whatever that may be. Then log of determinant is same as trace of log, and taking the log and derivative becomes trace of inverse, and then some kind of a derivative of K. So either involve, so this part is similar to this one. So knowing that the K is an integral operator means that this result will also be similar, close to be an integral operator as well. And then using that one can do something about it. And more importantly, at least from the integral systems point of view, is that if K is an integral operator, and this resolvent can be obtained by solving the so-called Riemann-Hilbert problem. A Riemann-Hilbert problem is a complex matrix factorization problem. So something like this one. So the operator K, or the kernel of the operator K, there is a very easy way of associating a certain matrix valued function. Let's call it V. So V is a matrix valued function on the contour. A Riemann-Hilbert problem is to factorizing this V in such a way that they can be extended in the sectionally analytically. So we want to find a sectionally analytic matrix function Y of Z. This is analytic in complex plane away from the contour, so that on the contour, if you take a limit from one side of the contour and the other side of the contour, they are not equal. If they are equal, they're going to be analytic, but they are not equal, and then their jump is related by this matrix V. And this V was given in terms of K. So solving this Riemann problem, so given K, you produce V, and from the V, you somehow solve this Riemann problem and produce Y, and this Y will contain all the information you need to be able to write down the resolvent. So from the Y, you can write down this logo derivative of the determinant in a sense. Okay, that's a piece of information about the integrable operators. And then separately from that, there are results about integrable differential equations and Riemann problems. The many integrable differential equations like nonlinear Schrödinger or KdV or modified KdV, and those work as even though they are nonlinear, there are nonlinear transformations, which is a generalization of Fourier transformation. Furthermore, those transformations are equation-specific transformations that transfer the initial condition to a certain data, and then data evolves in a certain simple way. And then by taking the inverse nonlinear transform, one can get the solution back. That's the sort of very, very, very short scheme of solving the integrable differential equations. And the way of recovering the solution is by solving a Riemann problem. So in other words, if you have a certain integrable differential equation, then starting from its initial condition, you produce certain data by doing the nonlinear Fourier transform, and that data will be then encoded as a matrix function V, and then you modify this matrix V from the certain very explicit way that follows from how the equation evolves, and from that then new modified matrix valued function V, you solve the Riemann problem, and that will contain the solution to the integrable differential equation at a later time. So that's a scheme. So there have been a lot of work that, okay, which differential equation will give you which kind of matrix V, which kind of Riemann problem. So there's a whole zoo of charts of all these things. And so the kernel K, so there are two things now. So one is that integrable operators are related to Riemann problems, and then the integrable differential equations are also related to Riemann problems. And then it turned out, if you look at the kernel for the KPG fixed point or the periodic KPG fixed point, and then you look at what kind of matrix that is, and one can recognize as one of those studied ones, more or less. It's not exactly, so one has to do some work, but they share many features of nonlinear triangle or modified MKDV or KP equations, and then from there you can recognize how this should be satisfied or should be related to these equations, and then with some extra work, one can obtain those things. So, right. So one is using some kind of index page that one has this whole list of things, and then check it, and it somehow happens to be there. Right. So that's Alice's story at the moment, and then what we are trying to do is that this is for the KPG fixed point, but there are actual finite time models, TASEP or PNG models, and Brownian less specific population models, and so on. And for themselves, should satisfy some differential equations, and identifying them may be interesting. That is still working in consideration. Right. Okay. So let me stop now, and then thank you for your attention.
Thanks, Jinho. So why don't we thank Jinho for a very, very nice talk. Could I open the floor for questions? I have a general question, maybe just to start off. The kernel K satisfies those three equations: the nonlinear Schrodinger equation,
right,
and the other two. Is there so? Is that a characterization of the kernel K, or is there could there be other kernels K which satisfy those three equations at the same time?
Mm-hmm. Right, that's right. So so this so I didn't write it here, but those kernels will have of this form, and this Fi and Gi's are so let me so this so for example F1 of U is of the form that so this kernel K should involve all the parameters X and T and H, right? And they will appear in F and G in a specific form, multiplied by a function which do not depend on these parameters. So they will appear as e to the for example, like a t times u cubed plus height times u squared plus x times u. So e to the cubic function of these three variables times some other function which does not depend on these variables. So as long as this kernel has of that structure, then the firm determinant of that will be always related to these equations. So there is a little bit of characterization like that. So there are these particular structures needed for the kernel. So this kernel will involve those structure plus this extra non-parameter dependent terms. So from the differential equation point of view, those non-parameter dependent terms should specify the initial condition of the differential equation. But at the moment, we don't have a general theory of what kind of data of the kernel corresponds to which solution of which initial condition of the initial the differential equation. That correspondence is not clear to me. One reason for that is that here the solutions are complex valued, even though the differential equations are real equations. So from the physics point of view, actual solutions, relevant solutions are all real solutions. But here we are somehow artificially making complex solutions. So that's a little bit strange. And that has not been studied well.
I see. Okay. Well, thank you very much. Are there other questions?
I would like to make a question. So something that is always puzzled me is that whenever we think that there is a universal object around, it kind of has the good taste to be integrable in some sense. So, I mean, I believe that that's what somehow this is the intuition behind these formulas. I mean, a priori for me, it's not evident at all that the periodic KPZ for fixed point, for example, should have an explicit formula. And the only reason I could imagine is that because if it's universal, then it should be somehow integrable in some sense. I don't know if you can say more about this type of intuition. I mean,
yeah, well, I mean, that's not clear to me. So yeah, so why should we have an explicit formula at all, right? Yeah. So the way that I think about this one is that from the integrable, even for integrable differential equations, if, for example, KdV equation is well known to be integrable, but in what way? So it's integrable if you think about the equation on the whole line. But the being integrable means that if you change anything, nothing is guaranteed to be integrable, right? So even for the KdV equation on the whole line, if you change the domain to be half line or periodic domain, there's no guarantee that it will be still remain integrable. So for each thing, you have to check whether that is integrable or not. So what was done here is that this KPG universality theory, whole line now through the last 20 years of work, now we know that it's integrable. But if you change the domain, say from the whole line to half line, is that still remain integrable? That's not obvious. One has to do it, and they have been work, parallel work, like a whole line case, that one can still do something. It's not as comprehensive as the whole line problem. For example, in the whole line, one can do TASEP and ASEP, but on the half line, TASEP, yes, you can do, but ASEP is much more difficult. But in the periodic model now, it's now starting to emerge that, periodic model is not obvious it's going to be integrable, but now we are seeing these examples illustrating that they are integrable. So yeah, so to your question, I don't know whether the limit should be integrable is not clear. It's just that we were able to check one domain at a time and were able to show that they were integrable. I think that's the status at the moment.
Okay, thank you.
Yeah, so I mean, so to my opinion, what was interesting was that for a long time, even the different initial conditions, it was not clear that the models are going to be integrable. It was done for step flat, or stationary. It's all done one by one. But then this big work of Quastel and Remenick and Matesky in about 4 or 5 years ago, and they were able to show that for entire general class of initial conditions, you still do have integrable structure. So that was a huge success. And then now we are thinking about other domains in a way.
Yeah. Okay, very good.
Are there further questions for Jinho? Well, if not, why don't we thank Jinho for a very nice talk, and why don't we meet next week then? So
Thank you so much. Thanks for the invite.
thank you, Jinho.
Thanks for your help.